In this video, we're going to discuss the MergeSort algorithm. Now, before we can discuss MergeSort, though, we have to learn an important helper function, which is just known as the merge algorithm. So the idea behind the merge algorithm is we have two sorted lists as input, and we want to merge them together into a single sorted list. So we have two sorted lists, so 2, 5, 8, 9, so it's increasing order, and 1, 3, 4, 6, also increasing order. Now we want to get them into one sorted list that has all of the elements, but notice we can't just take one and then the other, because 1 comes before 2, but 3 comes after 2, so we can't just take all of these and then all of those. We have to figure out what order to take from either list. Now, one of the advantages, because these things are sorted, is that we know the smallest element of all of the items has to be at the front of one of these two lists, right? Because they're both sorted, so the smallest element for these 4 is at the front, and the smallest element for these 4 is at the front. So one of those is going to be the smallest of everything, so all we need to do is make a single comparison between those two elements. So in this case, 1 is smaller, so we'll take that as the first element in our list. And what happens next is we're left with one fewer element up here, and we just do the following comparison. So now we have 2 new smaller items, and to find the second smallest, it's still going to be the smallest from one of these two lists. So now 2 is smaller, so we'll take that as our next item. Now 3 is smaller, so we'll take that. 4 is smaller, so we'll take that. 5 is smaller, so we'll take from that side. Now 6 is smaller, so what happens next is we've used up all of one of the lists. Since the other list was already sorted, we can actually just take the remaining items and just attach them in place. We get our final result, and everything is sorted. Now, it's important to note that this merge algorithm only works if the input is already sorted. So, let's take a quick analysis of the merge algorithm. So how much work does this do? It says right there, but let's actually see in the picture. We can actually see it a bit clearer. So the idea is we make one comparison here, and when we make one comparison, we take one item into our final result list. Then we do a second comparison, and we end up with a second item in our output. Third comparison, third item in our output. So in the worst case, if we're doing one comparison per element, then it's going to take n comparisons to get n elements. So in this case, since we had 8 elements, we had to do 8 comparisons in the worst case. Now, we can take a bit of shortcut when one of the lists empties out, but we can't guarantee that one list will empty out early on in this algorithm. So in the worst case, we just say O of n, we have to compare one comparison per element, so for all n elements, n comparisons. Okay, so we can take 2 sorted lists and merge them together in O of n time. Great. How does that help us sort things, though? If these things require to already be sorted, how are we going to sort anything? So to answer that, we talk about MergeSort. So the design of the MergeSort algorithm is similar to how Quicksort worked. So it's going to be a recursive algorithm that takes the input list that's unsorted and splits it in half. So it divides and conquers again. Splits it in half, takes those new sublists and splits those in half, and again until everything's super small. Once they're all very tiny, what we can then do is start merging them together in sorted order. So let's just walk through the example here. So we have our input list in no particular order, and we're just going to split that in half. Now notice, unlike with Quicksort, we're not going to do any comparisons before we do this split. So there's no relative ordering between everything on the left and everything on the right. We just took what was already on the left and put it in a smaller list, everything on the right and put it on a smaller list. Okay, no comparisons have happened so far. Essentially, it's one step to split those two things in half. And then we're just going to keep doing that. So we're going to split again, and then we're going to split it again, and split it again, and eventually we'll get to a point where all of our lists are empty or only have one element. And at that point, without having done any comparisons whatsoever, all of these lists are magically sorted, right? The list that just has a 7 in it can't be unsorted because it just has one value. Now, relative to each other, we still don't know how they should all belong, but the list itself, or each one of these individual lists, are sorted unto themselves. So now we have, instead of one list of n elements that's unsorted, we have n lists of 1 element each that are sorted. Okay. Now what we need to do is bring these lists together, and it just so happens we just learned an algorithm that would be very convenient for doing so. So, taking all of these length 1 sublists that are now sorted, we employ the merge algorithm to bring them back together. So a merge algorithm with 2 elements is somewhat uninteresting, so I'm going to skip through this first step. So it compares 7 and 4, takes the 4 as the smallest, and then the 7 as the next smallest, so we get the list 4, 7. Similarly, 1 and 6 gives us 1, 6, 5 and 2 gives us 2, 5, 9 and 8 gives us 8, 9. So we've merged together one stage of that split tree that we just saw. And then we repeat again. So now we have sublists that are, notice they're still sorted order, because our merge algorithm keeps things in sorted order. But relative to each other, they're not. So we have to go through another merge to figure out what's the smallest item, what's the second smallest, what's the third, and what's the fourth smallest item. So we merge those back together, and same over here. So 2, and then 5, and then 8, 9. And now this, I believe, is pretty much the same example we saw earlier, where we have two sorted sublists, and we want to bring them together in sorted order. So compare 1 to 2, 1 is smaller, so we take that. Then we compare 4 to 2, 2 is smaller, so we take that. Compare 4 to 5, 4 is smaller, so we take that, etc., etc. Walking through the merge algorithm brings both of these things together back into sorted order. So we split everything apart without doing any comparisons whatsoever, and then once we have all those tiny lists, we run them together with the merge algorithm, and we get our sorted list. So, before we discuss the details of this, let's create some code, shall we? So let's go back to our Visual Studio page here, and let's say MergeSort.py. So for MergeSort, we have to create two separate functions. We have to create a merge function and a MergeSort function. Let's start with the merge function, def merge. So merge takes in two sorted sublists, so we'll call them L1 and L2, and it wants to sort them together, merge them together in sorted order. So let's walk through the design here. So we're going to start with an empty result list. So our output's initially just an empty list, and we'll walk through these two lists. So repeatedly, while both lists have elements, what we're going to do is compare the first element of each list to find out which is smaller. So compare the first element of each list, and when we find the smaller, we'll append that to our result. So append the smaller to the result. Now, that's going to happen a bunch, right? We're going to take the smallest and append that to the result, and then we'll come back up here and do the same sort of thing. So I should also mention, compare the first element of each list. I should say pop and append the smaller. Popping so that our lists get smaller, and append so that our result gets bigger. So we want our input to shrink while our output grows. This here now should eventually become false. While both lists have elements, initially we'll say we have elements for our lists. We compared and popped, compared and popped, compared and popped. Then one of the lists should eventually empty out. So if we get down to the end of this loop, one of the lists is empty, but we don't necessarily know which one. So we'll say one list is empty, so add all of the other list to the result, and then just return the result. Okay, so if we've popped all the elements out of, let's say, L1, then what's left of L2 is already in sorted order. We can just attach that to the end of our result. So let's fill this up with some code then, shall we? So start with an empty result list. We'll even just call it result equals, and then an empty list. Now, while both lists have elements, so we want a while loop, and to say that one list has an element, we'll say the len of L1 is greater than 0. We want that for both of them, so and the len of L2 is greater than 0. Now, if either of these things becomes false, so if L1 has 0 elements, that makes the entire thing false. Oh, geez. And then that'll break out of the loop. So next is compare the first element of each list. So that's just an if statement. If L1 at 0 is less than, or say less than or equal to, because the equality has to go somewhere, is less than or equal to L2 at 0, then what we need to do is pop and append the smaller to the result. So we want to remove the smaller element. So if L1 is less than L2, if the first element in L1 is less than the first element in L2, then we'll remove its first element. So we'll say result.append L1.pop 0. So remove the first item from the first list and append it to our result. Now L1 got a little bit smaller, so this condition got a little bit closer to false, but we're going to go back up and repeat and repeat and repeat. Now, if this is not the case, if L1 is not the smaller, then L2 must be the smaller. So else result.append L2.pop 0. Now guaranteed one of the lists got smaller each time through this loop, so we're guaranteed to not have an infinite loop. Eventually these things will become false, one of them will become false, and we'll make it outside of the loop down to here. At this point we have one empty list and one list that may still have elements in it. It has to have at least one element because we're only removing one at a time, so we couldn't have emptied them both at the same time. So let's figure out which element or which list is empty. So we'll say if the len of L is equal, L1 is equal to 0. So L1 is the empty list, so we'll append L2. So we'll say result equals result plus L2. You can also use the extend function, but we're storing it in the same place, so it looks the same in the end. Okay, so if L1 is the empty one, great, we'll append L2. If it's not, then one of them still has to guaranteed be empty, so it must be L1, or sorry, L2 is the empty one, so we'll append L1. And then we can just return result either way. Okay, so this is the merge. We start with two sorted input lists and an empty output. We'll take one element out of it at a time, the smaller element at a time out of the two input lists, appending it to our result. Eventually one of those will empty out, and we'll append all of the other one onto the result and return everything. Let's test this out before we go any further. Python-i MergeSort.py. So actually just use, I need new lists. I'll say merge, let's make constants here. So I'll say 1, 3, 5, 7, 9, and 2, 4, 6, 8, 10. So all the odd numbers, all the even numbers, so they should intermingle quite a bit. And we get 1, 2, 3, 4, 5 through 10. So seems to work. Okay. So that's our merge algorithm, but again, that doesn't sort things for us, so we need to create a MergeSort algorithm as well. And that just takes in an unsorted list. So the steps for MergeSort are actually a lot simpler. Once we have the merge algorithm, that ends up doing most of the work for us. So MergeSort's a recursive function, so it needs a base case and a recursive case. The base case in this case, as we saw from the picture, is when the list gets so small that they're sorted unto themselves. So list has 1 or 0 elements, we can just return the list. Okay, so if it has 0 or 1 elements, it's already sorted. So if the len of L is equal to, less than or equal to 1, return L. Just like with quicksort. If we get to the base case where our lists are so small, then we don't have to do anything. Now, if it's not that, then what we'll need to do is split the list into two sublists, just around the midpoint, doesn't actually matter. And then merge sort both of those halves. So each one of those lists needs to be sorted, so we'll say merge sort both halves. Now, once those things are merge sorted, the both halves will be sorted at this point, right? We'll pass in unsorted halves, we'll get back sorted halves. Still have to figure out how that all works with our merge sort algorithm, but assuming merge sort will eventually work, this will give us back sorted sublists. Then the only thing we have to do is merge those sorted sublists. So merge the sorted halves and return. That's it, just 3 steps after the base case. So split the list into 2, merge sort the halves, and then merge the 2 halves together. So first things first, split the list into 2 sublists. So we need 2 sublists. We also need to know where the middle is so we can split it. So let's start with calculating the midpoint. Now this list that comes into this function is originally the entire list with all, let's say, 1,000 elements, but then when we call it down here with merge sort, it's going to be a smaller version of that list. But we don't have to worry about the start and end being in weird spots because we don't have a specific part of the list that we're dealing with like we did when we were doing binary search. In this case, if we want the middle, it's just the middle of the list, so the len of L floor divide by 2. Roughly the middle, plus or minus 1. Okay. Then we need 2 sublists. So if we have this as our entire list, and we know the midpoint, then we can just take a slice up to the midpoint and a slice after the midpoint to get our 2 halves. So we can say left equals L from the beginning up to mid, and right equals L from mid to the end. Okay, so it's everything on the left goes one way, everything on the right goes the other sublist, and then we just need to merge sort those 2 halves. So we can say left equals merge sort left, and right equals merge sort right. Now, assuming merge sort does what it's supposed to do, after this line, by the time we get to line 35, left and right are now sorted sublists. They're the first and last half of the input list, and they're sorted. So all we need to do is pass that to the merge algorithm, and it can do the rest. So we'll say return merge left right. Right? Merge takes in two lists, as we saw. If they're sorted, it will merge them together in sorted order, and we'll return that. So looking at one instance of the merge sort, or one pass through this function, it might seem like we're not doing a lot, right? We're just splitting it in half, asking merge sort to do everything else for us, and then merging them back together. But if this code doesn't make sense, go back to the tree and make sure you understand how splitting this thing, and then splitting again, and then splitting again, and then splitting again, and then coming back and splitting again, until we get down to that base case, eventually makes it so that we have everything in sorted order. And then from there, we're returning left, which would be one item, and then right, which would be one item. We merge those together to get two items. And that returns back into, let's say, this call, so that left now has two items. Similarly, right will get two items, and then we'll merge them together to be four items. So go back to the tree, make sure you understand the algorithm, how it works, and how it translates into this code. So let's test this out. Do I have a list still? There's our list. And we'll say merge sort L. And there we go. List back in sorted order. So that's the code, but how can we understand this code? Now, I kind of mentioned, I believe, at one point before that we already know the runtime of this because it's the same as quicksort, but let's take a look if we can understand how it's that. Yeah. So think, actually, let's go back to the beginning of this tree here. So we started with our input list that was an unsorted list, and we split things in half, and we split things in half, and we split things in half, okay? So to split things in half does not take a lot of time. So we have this list, and we want two sublists. That's essentially one step to get this half, one step to get that half. So two steps. The thing that takes most of the time is bringing everything back together. So if we're doing a merge, we know a merge takes O of n time. So for this highlighted section here, n would be 2, and it takes one comparison to copy the 4, and then another step to bring that 7 over. So n time there, and then another n time here, another n time here, another n time here. So if n was 2, that's 2 plus 2 plus 2 plus 2, which is 2, 4, 6, 8. Okay. Notice 8 is the number of elements total across the entire list. Now, if we have n as 4 at this layer, it takes 4 comparisons to merge things together, roughly speaking. So 4 to merge these, and 4 to merge those. 4 plus 4, again, 8. And then to merge these, we have a total of 8 elements. So O of n time to merge these things together takes another 8 comparisons. So it didn't matter which stage we were at. If everything was down individual parts, or if anything was in pairs, or if it was in half the entire list, it was still O of n time to do a merge at each stage. And that's what this is saying here. Doesn't matter which stage we're at, it's going to be n total comparisons, roughly speaking, in the worst case, in order to do one layer of merges. So we have n plus n plus n. And the question is, how many layers do we have? So n times what to give us the total cost? So if each stage is n comparisons, how many stages do we have? And that's best seen, again, through this tree here. So if we have n elements, we divide it in half, then we divide it in half, we divide it in half. So the height of this tree is the number of times we can divide something in half. Let's say the number of stages we have is how many times we can divide n by 2, which, as we've seen in previous lectures, is the definition of log base 2 of n. So there's log n stages, and each stage does n work. So grand total is n times log n, or n log n as it's called. There it is. So at each stage we split in half, so there's log n stages. Each stage we do n comparisons, so O n at each time, so n times log of n gives us, again, n log n comparisons. Now, the nice thing about MergeSort is that it isn't based on randomness at all, right? If you think back to our quicksort video, we saw if we take very bad choices for our pivot, then our list is not going to shrink by half at each time. It's going to shrink by 1. So then it's going to end up being O of n squared. in those very unlikely random scenarios. With MergeSort, it doesn't have that. The worst case upper bound for MergeSort is this n log n. It's not going to ever just have a sudden bad instance where it made some bad choices and all of a sudden it's going to be n squared. MergeSort will always be n log n. And this is why it's the industry standard for sorting algorithms. In fact, the Python algorithm, when you say list.sort, which is here, we still have L, yeah. I just say L.sort here. That sort's in place. It's a little bit different than the MergeSort we learned because it's actually in place rather than returning a new sorted list. But it's the same process, the same algorithm. This actually uses the MergeSort algorithm as part of it. It uses what's known as TimSort, which is a combination between MergeSort and I believe it was insertion sort. So the idea being, with each call to MergeSort, since it's a recursive function, it's calling itself with smaller and smaller lists, the overhead of those function calls eventually becomes more than necessary. So when the list gets small, let's say around 3 or 4 elements, it's really quick to just do a regular n squared sorting algorithm. For such a small value, n squared isn't that big. So when the list is very large, we'll use MergeSort to split it apart and split it apart. But the base case will be a little bit different. We'll say if the len of L is less than 5, then return insertion sort of L. And then we'll return that rather than waiting until we get down to those base cases where it magically sorts itself. So in practice, that does run a little bit faster, so that's why Python uses a combination of 2. But as far as you guys need to know, MergeSort is the best algorithm, so that's what you should be using. All right, I think that's it for this lecture. So I'm going to end this video here, and this is also the end of our recursion lectures. So I'll talk to you next video.